Our first session in the Aerospace and Defence track is an industry keynote on meeting artificial intelligence needs of today's military embedded systems, courtesy of Mr. Tran, VP Global Marketing at Aitech USA. Please welcome Mr. Tran.
Hello, everyone. Welcome. My name is Tran. I'm Vice President of Global Marketing at Aitech. Today, I'll be talking about artificial intelligence needs in today's military embedded systems. I'm going to be talking about a few trends and how it impacts the military embedded systems industry. First, some of the top trends that we see in the military embedded electronics. The very first things that we see is the accelerating need for computing power, particularly AI and machine learning. These are some of the things that we see everywhere. It has proliferated all industries, and the militaries and space and aviation industry is no exceptions. And this is one of the biggest trend that we see. But there are many other trends that I have on this list here that's affecting the industry. The other one is protection from cybersecurity. So when you have many systems connected together with edge computing, you are more susceptible to cyber attack. That's the second trend that we see affecting the industry. The third one is militarization of space. So AI is now also penetrating into not only into the military, but also it's gone into space technology as well. The next things is not a new trend, cheaper and faster. I think you also see an acceleration of this trend of cheaper and faster systems. And COTS in space is also a very important, and it's also another thing that's accelerated. It's gone from what used to be a novelty, and now it's a necessity. And COTS means a commercial off-the-shelf product. And this will not be possible. AI application will not be possible in today's world without the COTS everywhere. The other thing that we see is a tighter footprint with more functionality in terms of SWaP-C, so size, weight, power, and cost. This is another trend that we see accelerating. Things are always getting smaller. Things are getting more powerful, and the next one is wider adoptions of open standards. A lot of the standard that I'll be talking about in a little bit is such as SOSA, such as FACE. These are open standard that is driven by the US DoD, but now it's affecting the military applications globally. As the world is very connected, particularly among allied countries. And so open standard is widely accepted everywhere. The last two trend is around a small and light and fast unmanned solutions. So you see that there's a lot of unmanned solutions. Everything it's you have UGV, unmanned ground vehicle. You have a UAV, unground air vehicle. And the last trend here is supply chain flexibility and agility. One of the things with COVID that's made it very clear is that the supply chain of rugged military electronics it's disrupted, and there's also a change in the in how the defense industries is conducting itself. So these are some of the trends that we see affecting in today rugged military systems. Now, to be able to achieve AI applications in all different areas, what you see is there's different level of ruggedizations from everywhere. What we have, if you can start with a consumer or commercial component from AMD or Intel or NVIDIA, some of the top players in this, as you move up into ground vehicle, into air, into very high altitude, or into space, you are looking at a very significant ruggedizations level. A ruggedization simply means that the ability to operate in the environment that is very different. Whereas a consumer product, Your environment operation is fairly simple. You just use in your day-to-day applications. But when you go into military applications, the ruggedization is very different. And the other thing is, the higher you move up in the ruggedization level, the more tests and requirements that you have to apply, and also it's much more unforgivable once you move up for example, into space. In the ground vehicle, for example, you can if your vehicle stop working, you can just park it. While you're flying, you can't exactly park it. It's a bit more difficult. And if you're in space, you can't even bring it back. So it's a one-way trip. And so the ruggedization level for COTS is very different. And this is also why the cost, not COTS, but the cost of from the commercial to space is a very large. And you're looking at, for example, between ground and space to be almost a 10x factor. So just a very brief kind of ruggedization level for different applications. Okay. Now, if we look at the future battlefield, and this is what drives a lot of the need for AI into the future battlefield. If you look at this picture, for example, unmanned UAVs, robotics. Here you have a smart soldier, you have communications, you have satellite systems. What is the common thread in all of these is the AI application that is everywhere. You require to have AI applications when you don't have a pilot. You will require AI applications when you have comm systems. The other things is there's what's in common in all these things is the fact that all these things needs to be real time. And this leads to one of the first trend, which is the rise of parallel computing. From the previous picture, you can see that if you use traditional serial computing, what you have on top here, you will have a hard time operating in real time. And so there's a big trend is move towards more GPGPU like processing power, which use parallel computings, because things needs to be real time. The information needs to happen immediately. Decision needs to happen right away. And so this is what drives the rise of parallel computing that we see in the embedded industry. And this is an example of GPGPU-based systems. You use parallel computings to do drones, man-made portable, wearables, UAV, communications, and all these things. And also it goes into space applications. The second things that we see affecting quite a bit once you have everything connected is the fact that cybersecurity is becoming a major threat. When everything is connected, when everything has edge computing and all these systems, you are much more susceptible to cyber attack. And cyber attack can happen anywhere in the life cycle. It could happen during the design phase where they steal the design. And it can also happen during the deployment where they can take control of your drone, as an example. And to protect against cyber attacks, what we do, the industry is adopting is a lot of a commercial software as well that is adopted for the military and space applications. As you have more of these devices connected, you can see from this list here, for example, authentication of software, programmable logic device, and all these things. Okay. The third trend I wanted to mention to more details is I've alluded earlier about COTS and COTS being from a novelty to a necessity. And the benefit is it's very clear. I think you're able to do things in months as opposed to years. It's also much more reliable as well. It's proven to be having decades of reliability in the field. And also it makes it much more affordable. So without COTS, it's really not possible for where we're going. The other trend is the not only COTS it's used in military applications, it's also now accepted means to be in space as well. And in space, the benefit is even more even more stronger. You're looking at a 90% cheaper compared to a custom system, for example. And at Aitech, we're a pioneer of cotton space, and we have 30 years of being in space without a single failure, flying trillions of miles. And increasing computing power in a shrinking footprint. What we see, you have two ways of doing this. You have more for the same or same for less. More for the same simply means that you add a lot more functionalities, a lot more AI processing power into systems that has a higher functionality into the same footprint that you have. And these applications, such as large UAV, UGVs, manned aircraft, tank, combat vehicles, and all these things. And for same for less, it simply means you don't need more processing power, but you need to make them smaller, things that fly, for like small UAVs, robotics, military robotics, or smart soldier. These are the areas where you would require the same functionality. You don't need more, but you want to make the systems a lot smaller. So we see clearly there's a separation between the two types of applications, AI application that we see. One of the big enabler as well in our industry is the advent of industrial standard, both hardware and software. Some of the most common one now that is gaining a lot of tractions is SOSA, which is a common hardware standard, and FACE, which is a common software standard. One cannot live without the other. If you only have a standard and SOSA, and without the FACE, then you're not able to actively you don't achieve what you're able to achieve. The other one as well I listed here is a VITA standard as well. Okay. So what just deep dive a little bit on some of these open standards. FACE, I mentioned, is it's a software standard. It's a future airborne capability environment. It originated in avionics and has expanded to all others as safety critical applications. And you can see the militaries and space applications, nearly all of them are safety critical applications. So it's really penetrated the entire military, aerospace, and space applications. It is designed to be hardware agnostic with a common operating systems. Its main focus is on reuse and portability, so that each time you don't have to reinvent the wheel every single time. And it facilitates data transport between this different hardware. What is trying to achieve are better integration and interoperability issues, so that things can connect to each other from third parties and all these things. Also, it's much more sustainable and scalable. Unlike a lot of commercial product, when you build a military applications, you are in the field for decades, so 20 years, 30 years, 40 years, 50 years. And in that time frame, technology changes very significantly. So scalability is very important. By having a system that is scalable from the beginning allows you to build scalable systems. And well, also it's insertion of technologies. If you look at a fighter jet, let's say an F-16 from that came out first time in the late 1970s, or to the F-16 that's flying today, is not the same aircraft, even though it looks the same. So a lot of insertion technologies, applications there. And back in the day, they didn't have AI applications. And so you see a lot of AI applications going on board these systems as well. Okay. And the picture here, actually, I want to draw your attention to, without having to repeat everything, is this one. Is if you think about all the different hardware and having SOSA and FACE, it's simply having the same head ball interface. So that's the SOSA interface that defines you the shape that you can plug no matter what your application is into the systems. And then the face allows the software to be able to work as well. So it's the same idea as using a light bulb to be able to change applications as you move forward. And also all these applications changes a lot with time, with technologies and everything. But the interface is always the same. And that's really is the guts of what face and SOSA, those two hand in hand allows you to do. Okay, for interest of time, I'm gonna skip this slide a little bit. But the two things that SOSA and face works really well together is in the operating systems and the transport service segments. So what happened when I talk about all these trends and we talk about AI penetrating everywhere and open standard and COTS and tighter footprint and better supply chain. What does that all lead? All these things lead to is a concept we call a digital backbone. And there's a very innovative yet simple concept as well. And we use the human anatomy as a bit of a proxy to understand this. You have the brain, which is the processing power, and the memory units. You have the sensor, which are the inputs, and you have the actuator, which are the output. Currently, what's happening today is that the actuators, the sensors, plug directly into the brain. The problem with that is it's not very scalable. The problem with that is you cannot add third-party systems. Is that every single time you have to redesign the system from scratch. And that has massive implications into what you cannot do in the future. It's not future-proof at all. The idea of a digital backbone, and instead of plugging these things directly into brain, is you plug into a kind of a digital highway, digital backbone, where you can add more sensors, you can add more brain power, you can add more actuations as you move forward. And this is what all these systems, all these trends combined leads you to a concept such as a digital backbone. So let me talk a bit more details into the digital backbone and what it is. What it is it's a common digital communication infrastructure, kind of a highway that sits between the brain, the sensor, and the actuators. And it moves data from the sensors to the processing units. It moves from here to here. It moves the processing unit to the actuators. And it moves between processing units and memory storage as well as you add more systems. And you can clearly see the benefit is that you don't have to reinvent the wheel every single time when you do that. And we can also design the requirements for specific use. So you can, and each application can use the same architecture, but the components and what you value as a requirement can changes very drastically from one requirement to another. We can consider swap C, performance, synchronization, scalability, reliability, availability, the right ruggedization level. Is it used in space? Is it used underwater? All these things change the type of component that you do, but the common architecture allows you to tailor fit your requirement for specific cases. And the benefit is also that is a system that is pre-integrated and fully verified. I talked earlier about the supply chain that is changing. What you see is that the whole supply chain in the military and the space and aviation industry is companies are taking larger subsystems because things are getting more complex. And so be able to pre-integrate and fully verify, it's a highly valuable. You can pre-integrate and verify switches, endpoints, data converters, and processing units like GPU, CPU, FPGAs, memory storage, sensor, cameras, frame grabbers. You can make the digital backbone kind of as simple or small as you want, or you can expand the digital backbone to something that is fairly complex. And then all these things is possible from all the trend that we see in industry, such as a open standard and all these things. Okay. And just example of where this digital backbone concept is penetrating, we developed that for the drone and small UAV market. We developed that for the vertical lift, for UGV, and for small sats. Now the concept is the same for each of these applications, but the component, for example, the swap C between the drones and UGV is very different. Whereas weight is really important here, weight is not so important here. Processing power may be more important here, or here, or here, and less here. It really depends on the applications that we see. And again, if you look at this picture here, a lot of these things doesn't have a pilot or human interfaces. So AI application is used everywhere, and it's really accelerating. Okay, so why doing this, and what are some of the benefits? Is significant reduction in cost and time. I mean, we're looking at an easily 50% reduction just in the development phase by having open standard use of cards. We can also, it allows to add third-party components. So Aitech doesn't have to just build a system based on Aitech components. We can have system from other vendors, either that we can add into the digital backbone. And also, even though the open standard came out of the US, what we see is that we see an adoption open standard globally. When somebody already have a standard, I think it's adopted, particularly among allied country, it's just easier to adopt a standard that already exists. The next point about flexibility, fast adoption, and the additional product, that's probably even a greater benefit of why using a digital backbone. Because any applications that we have today, 2 years from now, 5 years from now, 20 years from now, will not be the same. And if you don't design built-in right from the beginning, you will not be able to do it. And we know in technology world that the world moves so fast. Imagine 10 years ago, what was the world like for us 10 years before or 20 years before? Now fast forward that 20 years later on, we cannot imagine what application we'll have. And so we have to build in the foundation to be able to do that. So this is even a much bigger benefit to us than just simply reduction in development cost today. And the third thing is also by pre-integrating and with and verifying security is increase their confidence and the whole systems before they get fielded. And so these are some of the major benefits that we see in the digital backbone concept. Okay, so my presentation is coming to an end. Just wanted to say a few things about Aitech for those who don't know us. We are a global company based in the US, in Israel, and in India. And we've been in the rugged industry for the better part of 3 decades. At Aitech, we also have a very large global customer base, and you can see here we have a customer international list of companies in the defense and aerospace electronics, and we have a long list of distinguished customer worldwide. You can see some of the big names here: Boeing, Airbus, Collins, AIA, Raytheon, amongst others. And this is only a small list of customers that we have. And feel free to reach out to us if you have any questions regarding this presentations, or you have any question about the digital backbone, or simply reach out to us, or any other questions. We'll be more than happy to answer you. And I want to thank you all for joining and listening to our presentation. And thank you very much, and have a good day.
Thank you, Mr. Tran, for that informative session.